Amplifier damping factor. What is it, and how does it affect the sound of your loudspeaker? I'm Professor Fiore, and I'll explain it to you right now. All right, so just what is an amplifier's damping factor? Well, for an audio amplifier, damping factor is defined as the ratio of the nominal impedance of your load, like your loudspeaker, so typically 8 ohms in a home system, to the amplifier's output impedance. So because this is ohms over ohms, you wind up with a pure number. In other words, there are no units. Now, the term damping factor is applied elsewhere, for example, in resonant circuits and filters. So this definition is a little bit different, although they are closely related, as you will see. So damping factor is just basically nominal Z load over Z out of the amplifier. Now, the lower your output impedance on the amplifier, the higher the damping factor. And high damping factors are generally considered to be desirable. If you have a reactive load like a loudspeaker, you got a dynamic loudspeaker, having a high damping factor, a low Z out, will allow better control over the driver. In other words, your woofer is not going to be able to sort of flap around as much because of this very low load impedance. And this is due, as you will see, to the resonant equivalent of a dynamic loudspeaker. So a rule of thumb for high quality performance would be maybe a damping factor of 50 or more. And that's going to turn into maybe a Z out of about 1/10 of an ohm, ballparking it somewhere in that area, as you will see. So let's go boldly forward and look at the effects directly. So what I've done here is I have a simple dynamic loudspeaker model, and there's a video on exactly how to create these. You can check that out. I've used this before for other purposes, but essentially the thing I want to focus in on initially is this part right here, right? So these are electrical equivalents of mechanical characteristics. In other words, the springiness of the air trapped inside the enclosure, or mechanical friction that we would have in that moving assembly, things of this nature, right? This creates a parallel resonant circuit. The more, let's call them mundane aspects, are like the resistance of the voice coil and the inductance of the voice coil. Those are sort of direct. But it might not be immediately apparent that part of this is a parallel resonant circuit. And what we know about parallel resonant circuit is it has an impedance peak. It starts low, comes up to the resonant frequency, peaks the impedance, and then drops back down. And resonant circuits like to ring. So what happens if we have a low Z out? Well, the woofer is just going to sort of ring, kind of like a bell. It just goes back and forth, or maybe like a pendulum or a swing on the playground, right? It's just going to go back and forth at its preferred frequency, its resonant frequency. So we can help control that with a low Z out. So I'm throwing in a Z out here of 1 ohm on my voltage source. So my ideal voltage source internal impedance is 0. So basically just setting this resistor will set the output impedance of the amplifier. Now I'm treating this in the simplest case, which is purely resistive value that doesn't change over frequency. In reality, the output impedance of an amplifier is not necessarily purely resistive, and it's not necessarily fixed across frequency. But that's also true for your loudspeaker. We're using a nominal calculation here. In other words, we're going to say, oh, this is a home loudspeaker. It's a bookshelf loudspeaker. So, it's 8 ohms. Well, if you've seen my other videos on loudspeakers, that's not the case. That impedance could be 4 ohms at DC. It could be 30 ohms at the resonant frequency. Drop back down to maybe 4 or 5 ohms, and then start increasing so that it's 10, 15, 20, 25 ohms at high frequencies. All right, so this is a really dynamic system. So really, when we talk about damping factor, the way it's calculated is just nominal Z over the Z out. You know, we're looking really more at a rule of thumb than a hard and fast, super accurate value, right? So we just want to kind of look at this in more sort of qualitative terms rather than hard quantitative terms. But that's okay. That gives us some insight. All right, so let's do a quick transient analysis on this. Now, I'm throwing in a 1 volt peak square wave, 100 hertz. So, you know, if everything was perfect, what I'm calling V woof over here, because this is my woofer model, this should also produce a nice square wave. It will, of course, be a little bit lower in amplitude because we're going to lose a little bit of the signal on the Z out, basically forming a voltage divider, right? There's a voltage divider between this Z out and this. And that would be the case, you know, if we just had an 8 ohm load out here, you know, we would lose, you know, a percentage, 10, 12%, something like that, on the Z out. We'd get the balance, you know, 90-ish% out here. But like I said, this is a dynamic system. You know, this is not just a simple resistor. So what do we wind up getting? So I'm going to do a little transient response. I'm going to skip the first 10 milliseconds, which would be basically the first cycle of the square wave, because I want to get past the initial startup transient. And here we go. All right, so the green is the ideal, in other words, my ideal amplifier's output, and the maroon here is what's actually being fed to the woofer. In other words, Z out is not just limiting, you know, a certain percentage of the output and everything scales. You can see that this is not a perfect square wave. There is this sort of funky dip ring thing happening here, okay? Now, that effect, you know, if it's particularly pronounced, it's going to be quite obvious. It's going to lead to boomy bass. Now, to show you what you could get if you had a lower Z out, right? Here, it's really easy to do. I'm going to put in factor of 10 improvement. I'm going to bring this down to 100 milliohms, 1/10 of an ohm for my Z out. How much more control do we get? Well, we get that much more control. Compare these two things. 1 ohm, 0.1 ohms. It's pretty obvious that the 0.1 ohm, the low Z out, the high damping factor, is a clear improvement. It's a clear improvement, all right? Now, you might be saying, oh, wait a minute there, Professor Fiore. I'm not just going to hook up my woofer directly to my amplifier. Well, actually, you could. If you have an actively crossed system, you know, like a biamp triamp system, that's exactly what you would do. And for those of you who have seen my other videos on active crossovers and so forth, you know that I'm a big proponent of that route, even though it is admittedly more expensive. It has proven advantages. You would come back and say, you know, I have a crossover in here. Is that going to affect things? No, I in a real world loudspeaker, right? I have the output of my amplifier, which is here, coming into, you know, the box, the loudspeaker, bookshelf loudspeaker, let's say. And the first thing we see is a crossover network, you know, an RLC crossover network to split the frequencies up into the various drivers. And then out of that, we have the models for our loudspeakers. Okay, you know, that's fair enough. So let's go look at that same thing, but we're going to include a typical crossover for the woofer. What I have here is a third order Butterworth low pass filter, and I've tuned it to 2 kilohertz. So I'm assuming I have maybe like a two-way system, right? So I've got the woofers running 2K down, and then I have some manner of tweeter running from 2K up. And to be honest with you, you know, the precise value here doesn't make a whole lot of difference. So 3 kilohertz, 1 kilohertz, 4 kilohertz, it all depends on what you have for the high frequency driver and the capacities of your woofer. But just to illustrate, right? So this is a purely passive, right? 2-inductor capacitor, third order Butterworth low pass filter. How does this affect the response? Again, I'm going to go back to that 1 ohm resistor that we had. So this is the relatively low damping factor, a damping factor of approximately 8, right? A nominal 8 ohm, which is what this is, and 1 ohm for the Z out. So let's see what we get. Bonk. All right, so you can see that the ideal right here, this is the perfect square wave. The amp is the green, so that's this. And we see that sort of dip thing we saw, and then the woofer is the maroon, and we can see there's quite a bit of ripple, right? There's quite a bit of ringing on here. But I want to caution you, that is largely because of the crossover network. And you're saying, wait a minute, my crossover network produces ringing? Yes, it does. We can still improve this though, right? Because I'm seeing a little bit of ringing in here from the crossover, right? The effect of the crossover, I should say, how that loads the source with the Z out. And that initial thing we saw, that initial sort of dip, right? This thing, that sort of dip, okay? That initial sort of one bounce kind of ring. So we see those together. But let's go back and try to improve the situation. We'll go back to a 0.1 ohm. And we'll see what that produces. Wonk. Okay, so there's the green inside, right? And that's pretty nice. That's pretty flat. Now the woofer signal, right, which is back here, right? That still is producing the ring. And that's partly really two things. It's the inherent ringing that we get here, but it's also the interaction of that with this impedance, because this isn't just a nice 8 ohm load. So this interacts with this, and we get this extra ringing. So, how do I prove that to you? Well, let's replace this with the nominal value. Let's just replace this with the ideal, purely 8 ohm resistor load. So, if you were doing this in lab or something and you didn't have a loudspeaker and you just put a dummy load out here, this is what you'd be looking at. So what do we wind up with? So let's go back to the 1 ohm, do a transient analysis. And there we go. All right, so we can see, right, there's the ideal, my nice perfect square wave. What's coming out of the amp has that little bop in it. The big swing has been attenuated, but there's still a little bit of ripple here. But this ripple is not as bad, right? Look at the maroon there. It's not as bad as this. This is much worse. Because again, this is interacting with the load, okay? That would be the green version, which doesn't have much ripple. And then, like I said, if we go back here, right, we can see it's not nearly so bad. There's still a little bit of ripple there. And by the way, you know that this isn't at the resonant frequency of the model. In other words, the, let's see, there we go. The thing that's causing this sort of dip, the parallel resonant part of the loudspeaker, because this is a much higher frequency. It's easier to see here, but this is a much higher frequency than the resonant frequency. That particular loudspeaker, the resonant frequency is, if I recall, somewhere around 30, maybe 35 hertz. Okay, and this is a 100 hertz square wave. So this is clearly caused by the interaction of the crossover network with that dynamic impedance. Now, if you really wanted to, because you can see that the resistive version, right? Here's the resistive version. You can see that that behaves much better than the real loudspeaker, which is this one, right? So the real loudspeaker version being this. Now, if you've seen some of my other videos, you know that there is a way that you can kind of control the crazy impedance swings on here. You can do something called impedance correction, right? And what that will do is flatten the loudspeaker's peaks and valleys So you get something closer to an 8 ohm load. In other words, a nice ideal resistor. It won't be perfect, but it'll be much closer to an idealized 8 ohm resistive load. And you won't get these really sharp ripples that are the interaction. Okay, you'll get something closer to this. I'm not saying you'll get exactly this because the correction that you get is not perfect. All right, but you put a correction network in here and you can make this thing perform a little bit better. All right. Now, as I said a moment ago, you can get rid of a lot of these problems by just getting rid of the passive crossover and going to an active system. So you would have a low-level crossover, probably built with op amps, and then the output of the low-level crossover, the active crossover, would go to separate power amplifiers that drive each of the transducers. In other words, if you have a three-way loudspeaker, woofer, mid-range, tweeter, there's 3 amplifiers. Yes, it's going to be more expensive, but it's a much better controlled system, lower distortion, higher amplitude outputs. That's what you see in PA systems. That's what you see in professional monitoring systems. But again, the price, is deemed worth it. Is it worth it in your home system? Well, that depends on your own audiophile sort of hearing and how deep your pockets are. Okay, but it's clear from our little investigation here that keeping this impedance down is going to help. So a low impedance, in other words, a high damping factor, is going to get rid of resonance effects or mitigate resonance effects on your loudspeaker system. And that's, a sonic improvement. The question is, how far down do you have to go? Well, visually what we're looking at here is vanishingly small deviations once we got down to this 1/10 of an ohm, right? That's going to give us a nominal damping factor of 80, right? 8 ohms. This is the nominal impedance of our loudspeaker model, 8 ohms over 0.1, right? So there's a damping factor of 80. Now, one final thing I have to throw in here. In the real world, this situation is actually a little worse because your inductors in your crossover also have resistance. So they're going to exacerbate this problem. If you have really long loudspeaker cables, especially if they're small diameter, in other words, large AWG, large gauge cables, like a 24 gauge cable or something like that, that's going to exacerbate the problem as well. So that's another argument for keeping your cables relatively short and, a decent gauge. So, depending on how short they are, maybe a 14 gauge, 12 gauge, something like that would probably work fine. All right, great. So bottom line, keep the output impedance of those amplifiers low to control the resonance effects on your loudspeaker. If you can get that damping factor down around, 50, 75, 100, that's fantastic. You're going to have very good performance. Great. Okay. This is Professor Fiore saying, till next time, take care. Have a good one.